All right, thanks everybody for coming. Professor Shen is started this fall teaching at Yale, right? His research focuses mostly on algebraic geometry, and today he's going to give a talk titled "Counting Rational Curves on K3 Surfaces and Modular Forms."
Okay, thanks for coming. As I said, so we start to record, right?
Yeah.
Okay, so as you see on this blackboard, I will talk about curves in K3 surfaces and modular forms. And in particular, this is a story first told us by physicists, actually, with this connection. So let me start with complex analysis. Okay, so I guess most of you have taken the course in complex analysis, is that right? Okay, so this is a common object to consider. So we use H to denote so those complex numbers whose imaginary part is positive. So this is the upper plane. So actually this H has a big symmetry given by the group so-called SL2Z. So this is actually the 2x2 matrices for the A, B, C, D. Satisfying this first A, B, C, D are integers. And the determinant, namely A times D minus B times C is equal to 1. Okay, so this is a group, and there is a natural action of SL2Z on the upper half plane. So I don't know whether this was introduced in your complex analysis course, but let's just review this briefly. So we have A, B, C, D acts on some complex numbers, and so this is the action is AZ plus B over CB plus B. Okay, I believe for some of you, it is not your first time to see this. Okay, so, but people, for some reason, people are interested in certain holomorphic functions on H, which have satisfied some symmetry properties given by this SL2Z. So interesting in functions, holomorphic functions. Well, here by people, I mean mathematicians. In general, people do not care about holomorphic functions. Satisfying this upper half plane, satisfying some set and symmetries given by this SL2. The symmetries given by SL2Z, and this actually leads to the notion of so-called modular form, or more generally of morphic forms. So this is actually a central subject in mathematics with connections to many other. So these things can be viewed as originated from complex analysis, but they have connections to geometry, number theory, and so on. Okay, so let me just give you a little more precise definition of what these functions are. So we care about functions which are in some sense invariant under this SL2Z, but if we only require that there are too few functions satisfying this property, so we release our condition a little bit. So we require that AZ plus B, CZ plus B. Well, this means you just take an action of some element to Z, and you roughly require that this is equal to Z. up to a correction term given by CZ plus D to the power k. So you put this term here, and such kind of function. So this is the central, the most important condition, and also you require some control of plus some technical condition, namely the boundedness of Fiz. So you just force yourself to consider functions when the when the z goes to like I x when x goes to infinity. So particularly when the complex number goes like in this direction, you force your function to be bounded. Okay, so this is just a technical condition. Roughly, you can think of your functions are those which in some sense invariant under this SL2Z action. Okay, so how do you find these kind of functions? It's a very natural question. How do you find these kind of functions? So for doing so, we can take a special element from SL2Z. So where's the eraser? Okay, so this seems to be a very complicated equation, but we can simplify it by taking. If we take here c is equal to 0 and d is equal to 1. So the reason for doing this is that now you really have this term being 1. And then you just pick, a and b to be. Okay, then what this condition says, it says your function actually is periodic. Z plus 1, there's no correction term, and this is equal to f. Z. So you have some periodic function, and this suggests that, okay, so maybe there's a natural way to construct this function by considering its Fourier expansion. So this suggests that we may construct such function, homomorphic function, by considering functions in the variable q, where q is equal to e to the 2 pi I z. You see, the intuition here comes from the Fourier analysis, but it's pretty natural in view of this condition, because if you have a function in a variable q, then what's the meaning of this condition? Namely, if f z plus 1, this means, so automatically this function will satisfy this condition, right? Okay, so now I'm going to introduce one of the most famous function there called the discriminant modular form. So we define, so there's a long history in the study of this discriminant modular form. It's the following. I'm just writing you the expression in Q. So this expression actually is pretty concrete. You just have the leading term Q, and you consider the product starting from n. So this is 1 minus q to the power of n to the power of 24. Yes. Well, and so the claim is that, certainly I won't prove it, but the claim is that this actually gives you a modular form. For k is equal to 12. So here you simply just rely on the choice of k, I'm telling you, if you do this and plug in q is equal to e to the power of 2 pi I z, then this is actually a modular form with k is equal to 12. So this k is called a weight. So in other words, this is a weight 12 modular form. Okay, so this, as I said, the study of this function has a very, very long history and a lot of legendary stories related to that. So let me just name one before we move on. So, okay, so let's now we have this expression, but we don't know, well, it's very concrete, but we can, nevertheless, we can just expand it, right? Well, so expand it, you know the first term is q, so the power starts with n at least 1. So you can expand this in terms of q to the power of n, where the coefficient is defined to be tau n. Okay, so you can just tau n is defined by this equation. Then there's a genius Indian guy called Ramanujan, probably have heard about his name. I think if I remember correctly, it's 1916. And he started to write down a bunch of properties without proof about these coefficients tau. There are many of them. Some of them were proven in a few years, and some of them were proven maybe after, 20 years after he wrote down these properties. And the most famous one, in some sense, the deepest one, is the following. Actually, if you consider the tau to, and you evaluate this tau at p, so for any p is a prime number, p is a prime number, then you actually have a control of this. And the bound is given by 2 to the power of 11 over 2. So this is a very weird number, which is called the Ramanujan conjecture. However, as you see, you have a very concrete Taylor series. You expand it, write it in terms of the q to some power, and you read the coefficient. And okay, so basically, I think it's a strict inequality, but anyway, so the Ramanujan conjecture that, okay, so the tau, if you look at certain coefficients, they have certain bounds. And this seems to be a very, something very elementary. However, this is harder than expected, and the proof of this was given, I think, in the 70s, after Pierre Deligne, who proved the Weil conjecture, and proved that this is actually reduced to a special case of the Weil conjectures in arithmetic geometry. So, so the only thing I want to say is that these coefficients are the study of these coefficients are super hard. It's harder probably than expected, and even for proving this prediction by Ramanujan, who made it in 1916, it requires a lot of deep mathematics. In particular, it involves a development of more than algebraic geometry. Okay, so now today I'm not going to talk about this one, but I want to do something weird. So instead of expanding lambda cubed, today I will expand 1 over, sorry, not lambda, delta cubed. Today I will expand 1 over delta cubed. So this is, so the first term is clear, right? It's 1 over q because the leading coefficient here is, so the leading term is q. Then, so you have the Laurent series, and if you do the calculation, then the next one will be 24. And then the next one will be 324 q. Keep going. Next one will be the 3,000 and 200. And then keep going. You can go to the beginning if you want. So if you just expand delta q is related to number theory, and in particular the world of arithmetic algebra geometry. But what's the meaning of these coefficients? I mean, this seems to be a more weird thing to do. Instead of considering the expansion of delta Q, I consider 1 over delta Q. And what's the meaning of these numbers? Well, this was found much later. I mean, the meaning of these numbers with the connection, as I just read my title, the connection to the counting rational curves in K3 surfaces. This was actually predicted by physicists due to their considerations in string theory. So today I will explain that these numbers actually, so this expansion actually is related to counting so-called rational curves in so-called K3 surfaces. Okay, so this is a takeaway of this talk. I will explain what's the meaning of this generated series. All right, so far I'm talking about complex analysis, modular forms, and some very complicated generated series. Then since I want to explain these numbers, 24, 224, and so on, I will do algebra geometry. So in particular, I will tell you what are so-called K3 surfaces. So K3, well, when I was a graduate student, I was wondering what name come from. So actually, it's not so clear. Some people said, okay, they are named after the 3 mathematicians Caleb, Kummer, and Kodaira. But some people say something else. But anyway, so they are called K3 surfaces, although they are, well, this is a stretch name, but they are very beautiful geometries. So before I introduce the K3 surface, let me do a crash course of algebra geometry, which basically covers all the things I have said in the class I'm teaching this semester. So not really true. Okay, so algebra geometry. So nowadays there is a very interesting trend that people try to make algebra geometry a very fancy subject, try to put all the fancy names on them. But for me, algebra geometry is just a very concrete thing. It's a study of polynomial equations. So the zeros of polynomial equations. Polynomials. And the way to consider the spaces so we need some playground where we can consider the zeros of polynomial equations. So these are called projective spaces. Quick question, how many of you have seen projective spaces so far? Oh, answer? Okay, so I will define a CPN to be, roughly speaking, lines inside, the space of lines inside C n plus 1. So you just consider C to the power of n plus 1. It's a linear space. You remove the origin, I don't like it. And then, well, it's a linear space, so just quotient out by C star. So C star is the non-zero elements in the complex numbers. So the C lambda, which lies in C star x on x1, x2, xn plus 1, this is, the action is just, you do the scaling action on every coordinate. Okay, so you have Cn plus 1, removing the 0, and then you consider the most natural action of the C star on this space and take the quotient. And this is an interesting space from many perspectives. For example, in algebra geometry, this is a playground where most of the stories happen. And in Sticky differential geometry, so this is a space with a very nice metric there. So anyway, I told you that this is it's a smooth, it's an n-dimensional complex manifold. think of this as some space which is very nice, where you can describe zeros of polynomial equations. Okay, now this is the playground, as I said. Then we can talk about the zeros of polynomial equations. But since we only consider points in Cn plus 1 up to scaling, the quotient of the scaling action, so we cannot consider the zeros of arbitrary polynomial, but we only have to consider the homogeneous ones. So then the zeros of polynomial equations inside Cpn are well defined. So, but for doing this, let's do a few examples. You see that actually they are connected to the things that we observed before, probably. The first thing is, what is Cp1? So, well, this is a one-dimensional, it's always a compact n-dimensional complex number. Okay, so the Cp1, okay, so you have something one-dimensional, and so let me just tell you, this is actually the one-point compactification of C. So you have a complex plane, and then wrap it up at infinity. So this is a one-point compactification of the complex plane, which is called the Riemann sphere. So the real picture of it is something like, right, so the space is, the geometry of the space is of this kind. You have a complex plane at one point, wrap it up. Okay, then, well, here basically I haven't written down any equations, but you can do a slightly more interesting one. For example, now we move to Cp2. So this is a two-dimensional space where, I mean, it's called a complex plane, a projective plane, because, well, two-dimensional is like a plane. So, and so we use the homogeneous coordinates x, y, z here. Now we can define the zeros. X squared plus y squared plus z squared is equal to 0. Okay, so we consider all points satisfying this equation. Natural question is, what is this? I'm going to leave this. So the answer is that actually, okay, so let's cheat and just by looking at it, well, this is something like complex, one-dimensional, but let's just consider this is a curve. Namely, I'm trying to write down something like a real picture. So it's a conic. So a conic inside, so the Cp2 is something like a complex plane. So let's draw this is the Cp2. And you have something degree 2, like a conic. And okay, let's draw a Cp1, which is a line inside Cp2. And I'm saying that basically this space is the same as Cp1. Why? You pick, since this is, this is a conic, it's of degree 2, so every line, you can think of, every line actually intersects with this space at 2 points. So you fix the points, the base point, and you start to draw lines passing through this point. And for every point on this conic, you identify this with a point on a line. Mm-hmm. And you keep doing this. Keep doing this. And you might be wondering that where this point is corresponding to, but Cp1 is not only a complex number, it's not only a line, but it has the infinity, so this point will be connected to infinity. So in short, I want to say that, so this is actually, so the picture of this one is also a sphere. Although it's embedded more in a more twisted way inside Cp2, but still it's a. Okay, so this is again the picture, a topological picture of the space.
Wait, are all conics going to be homomorphic or whatever to?
Yes.
Okay.
Yes. Smooth ones.
Smooth, yeah.
All right, good question. At least some people are paying attention. All right, so next one. So of course, now we have some feeling, but we can certainly make our life more complicated, right? So we can, the third example, and then we can consider qubits. Well, certainly I will not be able to do this forever, but the cubic one is interesting, so let me just try to show you what this should look like. Again, but you see this is a degree 2 equation. You can think of this as a degree 2 equation applied, but this is a degree 3 equation. So, all right, let's just draw a picture. This is a real picture. So, okay, so it's some degree 3, something like that. And okay, so again, we want to play the same game, right? We want to project things to a line. So this is CP2, this is a plane, and this is a line. So think of this as a plane. Two-dimensional stuff like this is a line. Okay, then again, you fix a point here, a base point, and then you start to project. And then what happens is this is no longer a 1-to-1 correspondence. It's 2-to-1. You draw a line which passes through this point, and there are 2 points which corresponds to a point on a line. And then if you draw another line that's also 2-to-1, you keep doing, it's 2-to-1. Right? So, but this seems to be pretty complicated. However, it's still, even from this picture, we can decide what the logical link looks like. Right? Now I'm switching back to the complex picture. So a line which is CP1 is something like that. So then by a direct calculation via this equation, we should be able to determine that how many points are the branch points of this 2-to-1 cover. So this is so we can count actual branch points, and by direct calculation using this equation, you will see that there are 4 branch points. So let's give it a name, C. So we have C maps to CP1, which is a sphere. This is 2-to-1 map. And you can count branch points. So you count branch points where this map is ramified. So count branch points. And then the number is equal to 4. This is not very hard parse. You can read this from actually the equation. So then, okay, you have, this is like a surgery, a logical game. So you just have a sphere and you cut this pass in pretty glue. So the outcome is that there is a torus upstairs. This is the 2-to-1 cover, where the 4 branch points are something like that. Where you can think of that this line as tangent to this curve. Okay, so you know this is like a donut. Yes, the pictures, or let me draw something like this. So you can imagine, okay, but you can play this game actually when you raise the degree of your curve. And I don't want to do this with you here because as you see, you can do this forever for infinite many degrees. But the idea is actually it's not that hard. You construct a branch cover over the Riemann sphere and you count the branch points. Then, in some sense, you can recover at least part of the topological information of the original curve. But as you can imagine that when you raise the degree of your equation, then the picture of your C will be more and more and more complicated. So okay, so far we have considered CP1 and degree 2 equations inside CP2, degree 3 equations inside CP2. Well, the next one might be CP3. I want to raise the dimension by 1. And we can consider, for example, here I'm considering degree 3, now I can consider degree 4. So this is a three-dimensional space. You consider points which are carved out by one equation. So this is a two-dimensional thing, namely a surface. So this is a K3 surface. Okay, so this is the first takeaway of this talk. So if you're asked what is a K3 surface, well, you just write down the Fermat-Quartic degree 4 equation, then this is a K3 surface. And definition. K3 surface is something which looks like this. A K3 surface is a complex surface or complex two-dimensional manifold, which is deformation equivalent to this. Okay, this seems to be, this is like a black magic. So you start with something very concrete. And then you can, if you do more mathematics, there's a way, so-called deformation of a complex structure. You can try to vary the complex structure. And all the K3 surfaces arise this way. But so the second step of it is like black magic, at least it's just convince you that they are, I hope this can convince you that these are very concrete geometric objects which look like this.
The old state CP2, right?
No.
No, okay.
You're allowed to, so this is a very complicated process. You can deform all, so you start with something in CP3.
Yeah.
You can deform the complex structure, but you may fail to be something, you may fail to be lying inside CP3. Actually, this is a very excellent question, and this phenomenon even can be seen in the case of curves. So if you consider a very high degree curve, say degree 5, then you can deform the curve so that it's not embedded into CP2. But anyway, so at least I can present it. One member of this family can be presented in a very concrete way. Okay, now this is the main character. Now I'll try to make the connection to the original equation, which is this one. So, okay, so how to do this? Let's explain what's the, so as I suggested in the title, we should consider the so-called problem called the counting rational curves in the case of surface. So, a rational curve in a K3 surface, let's call this X, S, and immersed CP1 in X. So you consider all possible ways for to immerse your CP1, maybe a Riemann sphere inside some complicated geometric object like this. These are the rational curves. Let me draw a picture. Okay, so this is a complex two-dimensional thing, which is in the real world is four-dimensional. So certainly I would not be able to draw this on a two-dimensional blackboard. But so just think of this as a four-dimensional thing called the K3 surface. What's the meaning of the immersed CP1? Well, CP1, so this is CP1 are something like sphere, and then it's just like you immerse your sphere inside X. So it could be immersed like smooth one. This is called embedding, or you can have self-intersection. So you have 2 points are identified after you met it. So this is, then if you, when you immerse it, where you have self-intersection, this is like, you glue these 2 points. So the picture is something like, oops, makes sense? You have a sphere, and you glue 2 points. Okay. And then actually you can have more complicated, you can have more complicated gluing, which happens inside X here. You have to consider all of them, and they are all called rational curves. Okay, so now we start with some ambient space called the K3 surface, and we consider the immersed CP1 inside it. And what I'm going to say is this actually recovers these numbers, 24, 324, and so on. But there's one idea that we have missed, which is that you want to produce infinitely many numbers here. So which means you have to have an index. You have to index the rational curves inside K3 surface some way. And for doing this, we require something called degree. So we will choose this. So if we just consider immersed CP1 inside K3 surface, we certainly cannot get infinite many numbers, but we have to consider a more refined problem. Namely, we want to count some specific immersed CP1 or specific rational curves, which are indexed by some integer. And when you make this integer vary, you get actually infinite many numbers, which will be corresponding to this infinite many coefficients of this modular form. And surprisingly, this was first told us by physicists from string theoretic consideration. And then mathematicians try to prove it, and then try to generalize it. Okay, so, all right, so let me explain what's the extra index which happens here. So this is called degree. So what I'm saying is that I want to answer this question: how to get infinitely many numbers so as I said, we'll consider degree. So as we consider, so what is that? Well, so this is actually, it's a new parameter. It's a new parameter. Okay, so the idea actually comes from very classical situation. So K3 surface is something which is a surface, it's two-dimensional thing. But we can consider the easiest of two-dimensional thing to try to get some inspiration. That's the CP2, right? So CP2 is the playground where we can describe zeros of polynomial equations, in particular, more precisely, the zeros of homogeneous polynomial equations. And when you consider homogeneous polynomial, there is a very natural invariant called degree. You can just talk about the degree of the polynomial. Yeah, so in this case, we can talk about, we have the degree of a curve C inside CP2. If you immerse your curve inside the CP2, then you have a degree, which is the degree of the corresponding polynomial equation. Okay, so this is due to the very special, the very nice property of CP2, but when we consider some more complicated space, how to recover this piece of data, or how to do generalization in that case. So this suggests that we can use some idea from topology, more precisely algebraic topology. So okay, so it's a natural question: how to think of a degree of a curve inside CP2? well. So at this stage, I have to use something slightly complicated called homology. So, okay, so how do you construct this? And we know that the homology of CP2, this is a abelian group. And if you have an embedded, if you have an embedded curve, then this actually presents a class here. And since this is a four-dimensional manifold, so there is something called intersection pairing. So this is the intersection pairing. Okay, so then the degree of your curve, I mean the degree of the corresponding polynomial is, so this is the same as the information of, let's give it a name, of this piece of data using algebraic topology. So this is the same as the self-pairing. So you start with some homology class on a four-dimensional manifold, H2, then you can consider the self-pairing recovers an integer. So roughly, this is d, then this is d squared in the case of P2. Okay. So, but it's the same. You can. So this means we can recover the degree. You have the tools in topology. In particular, that's why we, in college we have to learn more and more tools in mathematics because they are really helpful. And this piece of idea this idea can be used not only for CP2EC, but it can be used for any compact four-manifold, or maybe orientable, but certainly it's the case for K2. So this gives you actually the idea of the, so we can consider, for the same problem, we can consider H2 cross H2, which is the intersection pairing. And then we say that a rational curve, which is immersed CP1, C inside X is of degree D if its self-intersection is related to D by completely. So but I'm doing some normalization. If you use this tool in algebraic topology, this is given essentially like D. But we need to do some normalization, so this is actually 2D minus 2. Okay, so as I said, the upshot is that using tools from topology, it makes sense to talk about the degree of a curve inside a more complicated surface than CP2. And this is actually the missed piece we have, and then we can talk about the problem. So we define NP to be the number of the count of the number of rational curves. So degree 3 rational curves. In a K3 surface. So, and then this is so-called, now I'm going to give you a more precise formulation of the thing I'm going to, I mentioned at the beginning, this is Yao-Daslow formula, or, I mean, mathematician, at the beginning, mathematician and physicists, they consider this in different ways. So when they derive it, they use some physics. So they call it a formula. And for the mathematician, they are called conjectures. But now it's really a formula because it's proven. So, okay, so the conjecture says if you have an D, you make a generating series of D when you're starting with 0, 1, 2, 3, and so on. Then this is actually downward. So you have the first number is 24, and then the next one is 324 Q, and the next one is 3,200 Q squared, and so on. So this is governed by delta. However, this is not the question Ramanujan is interested because he considered delta, but now we consider 1 over delta. Okay, so this is the takeaway. So now, in some sense, I finished my mission here, which is I told you what is the connection, but now I want to give you evidence. So certainly I don't want to give you the full proof of it because this requires a little more, not little, but substantially more preparation. Okay, but I want to try to explain to you what's the idea of a particular, how to convince you something like this could be.
When was this proven?
Sorry?
When was this proven?
The first proven, I think after 10 years this conjecture was found. I'm pretty sure that I don't exactly remember. But, so, yeah, so this is a very long story. So, yeah, if you're interested, come to my office.
Okay.
But so the option is that first, well, this is always a question how to interpret the things predicted by physicists. So they wrote down this formula, and then when mathematicians try to interpret this, and there's there are a few layers, and then the first one, which is basically the form I'm writing down here, this is not so hard to prove. And then, but you can consider more and more general setups, and then the question starts to be harder. And so, yeah, so if you just want to consider the history of this problem, then it requires a lecture or so to define more, terms. But today I'm just going to focus on this identity. The one side is counting just rational curves inside the case surface. The other side is given by 1 over delta. Okay, so the last 10 minutes I'm trying to give you some evidence why this is true, in particular how tools in algebra geometry can help you to check this. Examples. But still, so far I was a little, I cheated a little. Because, so you see, when I was writing this, I'm using the quotation marks. So this means, so in order to make this number, to make sense of this number, will require a little more work. So namely, well, here's the question. You see that this H2 is completely topological, right? Since the H2 is a topological invariant. And certainly it's possible that, okay, so this is your question. In general, as I said, the K3 surface could be very complicated. It may not be embedded into CP3. And so the question here, the subtlety of the question here is that which K3 surface we are counting with, we are working with. Yeah, so mathematically there's a rigorous way for making this work. And let me just try to explain briefly this idea. So the H2 of a manifold or spaces, this is a topological invariant, meaning that certainly there's no class. So if you give a class here, an element here, it's certainly possible there's no things like, see, the curves, the immersed curves inside S, which present this class. It's certainly possible. So this means we cannot consider our K3 surface too general. Well, at least we have to consider K3 surfaces such that there is a class, at least there is a curve in the corresponding class of degree D. However, we cannot have this case-free surface too special. This is like when we consider problems in algebra geometry, so we want to consider how many points a conic and a line intersect. So if they're too special, then they could be tangent to each other, so there's intersect at one point. So in this sense, we'll have to count with multiplicity, which is too complicated. So in some sense, you have to consider case-free surface where it's not that general, but also not that special. So, but these, both of these two, both issues can be actually solved rigorously in mathematics using intersection theory. But this is not the topic for today. Okay, let me start with the first number, 24. How can we see this number 24? And actually, this gives you an idea how to prove this in the full generality. Just okay. So the question is, how to see 24? And I will finish the talk by explaining this. So step one is that now we want to count. So this is n0, right? This is a count of degree 0 rational curves. Then what's the meaning of that? So you only consider the rational curves whose intersection pairing. Oh, sorry. I may have to shift the degree a little. So the first non-trivial one is so the degree 1 rational curve. That is the case where C and the self-intersection is, you see that 2 times 1 minus 2. Okay, so then, as I said, step 1, how to find such a case-free surface where there are curves of self-intersection 0? Well, so you should look for something called elliptic fibration. So, okay, so generally, what's the meaning of that? Like C self-intersection is equal to 0. This is like you can move your curve freely. I mean, intuitively. This is in homology. This is like an intersection pairing. So this is like you can move your curve freely, and this is the case where your case-free surface admits a vibration over the CP1. So you have two-dimensional stuff, one-dimensional base, and then in this case, you know that a class of the fiber has degree 0. Agree? Because you can move this along the CP1. Okay, so for such a one, then how do you count this 24? Okay, so there are two steps. Basically, I'll finish this within this tiny space. So one is that from a general study of so-called elliptic, about vibrations of case-free surface, we know what the general fibers look like. So they are torus. So this is not hard thing to verify. You know, once it emits a vibration over a sphere, a general fiber has to be something like this, torus. And then, but these are certainly not rational curves. So, and it can move. This is of course of degree 0, but it's not a rational curve. So it only can occur at very special positions. That it's like a degeneration of your general fiber. So you see the general is like this, and in special you have this circle shrink to a point, and now this becomes a rational curve. Right? This is exactly the picture I wrote. You have 2 points on a sphere and make the blue. So this is the current picture. So this is called a degeneration of a torus. And now the question is turned to how many times in a family, how many times this will occur. And okay, so let me finish. So the idea is that we can consider, first we consider something called topological order number of your x. This is not so hard to calculate because you know this is a topological invariant, so you can just look at the quadratic x4 plus y4 plus z4 plus w4 is equal to 0 inside CP3. You calculate with this concrete equation. Then you can calculate that the number here is 24. And secondly, you explain actually this 24 are exactly given by these situations. Why? Because okay, so this topological space can be stratified over some complement of where this degeneration happens. And for this, every complement, complement, the fibers are torus. So then the topological invariance can be calculated as the topological invariance of a two-dimensional torus times some space, some manifold. I don't know, CP1 minus a bunch of points plus, and also a contribution of, and so there assume the number of M0 times the topological or characteristic of a degenerate one. So the total order characteristic contribution can be detected. So this is the general contribution, and then the contribution of this most degenerate one. So you finish because you see this is a torus. You don't know how many points you remove here, so you don't know. We don't understand this part. But you know for a torus, yes. So this is S1 plus S1. So its topological order number is 0. So 0, and then it's exercise to you if you're interested in topology. Convince yourself the order number is 1. If you, yeah, the way for thinking is that a sphere. What's the order number of sphere?
2 given, so like the 1 is 0.
It's 2.
2, yeah.
You can do a triangulation.
2, sorry, 2, yeah.
And then you glue 2 points, which means like if you do triangulation, you collapse 1 vertex. So it's like 2 minus 1, so 1. So 1 times n0, maybe n1, I don't know. So plus 0 is equal to 24, so you conclude that n1 is equal to 24. This is the explanation of the first term. And actually the full formula was proved this way, something like that. So the general idea is that you construct some space which is more complicated than X itself, so-called modular space. And then you first try to realize this ND in terms of some topological invariance of that modular space, and then you calculate this directly. And finally, you try to match with this arithmetic formula writing down here. Okay, so this is the end of the talk, and thanks for your attention.